Thank you. OK. I'm going to start by saying that GVT is officially retired, so it's time to stop using it and start using modules. OK, with the PSA out of the way, GVT was just a vendoring tool. OK, so we're going to talk about the net package today. So by a show of hands, I want to start by asking you, who used the net package? Not through something like net HTTP, but directly, like using net.Conn and the listeners and actually connecting, the raw connections. There's not a lot of hands, and this is good for two reasons. The first reason is that it means that the standard library is providing the higher level interfaces that you need to do your work without worrying about the lower level primitives. And it's a good thing because today we're going to go through an introduction of the net package, and we're going to build something with it. We're going to build an actual program that will be actually useful with the net package directly using the connections. But now, the talk is called Asynchronous Networking, but it will be a bit weird because almost everything we're going to do is going to be synchronous and blocking, because that's where the magic of the net package is. To understand what's so good about it, though, we need to take a step back and talk about how it used to work. So it used to be that if you wanted to handle more than one request at a time in a network server, you would just start a new thread, a new kernel thread, every time you get a new request. So a request comes in, and you make a new thread, and you make its process ID, and it takes a whole system stack that's 2, 4 megabytes, depending on how you set it up. And that really doesn't scale to 10,000 requests at the same time. So something that was developed over time is services that use something that we call an event loop. This is how Nginx works. Nginx is this extremely fast HTTP server that powers some of the biggest CDNs that serve a lot of the internet traffic. And how the event loop works is that all the work, the thread, there's a single thread, or maybe a couple threads, or maybe a pool of threads, but they're always working, trying never to block on network, so to never be idle. And to do that, they have an event queue of events coming in. And so an event comes in and can be, a new connection, or someone writing on an existing connection. And the loop will pick it up from the event queue, and it will start serving it. And it will do as much work as it can locally without blocking on files, without blocking on network. It will do as much work as it can, and then do some blocking operation like, OK, I have the response. I'm going to send it. And before that blocks, it will just tell the kernel, don't block. Just let me know later when this is ready. And then it will move on to another request, take another thing from the event loop, and in the background, there will be a poller that will check if those things that we're blocking have been unblocked. And if this sounds like a pain to work with, it's because it is. If you've ever tried writing plugins for Nginx, you're continuously saving the state and making sure that you don't block the hot loop on anything, because you're killing your server's performance as soon as you block. So now you have to take care of making sure that all the information about request 1 are saved somewhere, and they will be recovered when you start working on request 1 again later. That's no way to program. So enter Go. With Go, we write code as if it was just threads, where each thread is dedicated to a connection. But instead, they're not threads. They're goroutines. And goroutines are cheap, both in terms of stack and in terms of scheduling, because there's the Go scheduler, which will take care of essentially making the CPU behave almost as if it was an event loop, but you don't notice. Because every time you start a goroutine, that goroutine is going to serve that request, and it doesn't have to worry about saving state, events, queues, pollers, none of that. The net package has an integrated poller, so it will automatically get to know when the block ends. And when that happens, it will go into the goroutine, it will flag it as runnable, and every time another goroutine blocks, it will look for runnable goroutines, and it will spin them up. Which still sounds complicated, but the good thing is that we don't have to worry about it. Today, we're going to write code that uses all this, but it will all be under the hood, and we will have not to worry about it at all. So before we get right into writing something useful, we need to understand what we're working with. And we need to understand how the net package works. So the net package has a core fundamental interface, which is the net.Conn interface. Net.Conn is a connection which is connected to something else on the other side. It might be a TCP connection with a client on the other side that is sending us data. And that's what we're going to work with today. The interface has a few methods. It has read, which implements the IO reader interface. It has write, which implements the IO writer interface. Because in Go, interfaces are composable. You don't have to specify which ones you're implementing, you just have to do it. And then there's close, a couple things about addresses, and finally deadlines that we use to implement timeouts. We'll see how. Now, to get one of these connections, if we are a server that is accepting connections from someone, we want to use listen. And the other interface that we're going to care about is the listener interface. There we go. The listener interface is another core interface of the net package, and it has one important method that we care about. And that method is accept. Accept will take a new connection coming from the wire. It will block until that connection comes in. And when that connection comes in, it will return the connection and an error if something wrong happened with accept. So knowing these couple things, we can start accepting connections. So we're going to write code. This talk, we're going to write something from scratch. We have an empty package main, and we want to start accepting connections. So first thing first, we need a listener. A listener, we obtain it with net.Listen, to which we have to tell which protocol we want to use. And we use TCP because we want reliable delivery of packets. We don't want to care about packets that get dropped. We want the protocol to take care of that. And we need to tell it which address to listen on and which port. We're just going to pick one. Of course, if there's an error, we want to just exit here. And by the way, before anyone asks, this is not a magic character. It's just a ligature. It's a font. And it's just bang equal. OK. So now we need to write what's called the accept loop. It's a loop because we want to keep accepting new connections as they come in for probably the entire lifetime of the server. Because that's what it's going to be doing. It's going to be taking new connections that come in and service them. So we're going to obtain a connection and an error by calling l.accept. If there's an error here, technically you should check if the error implements the net error interface and make sure that if the error is temporary, you just give it a pause and try again. We're going to skip that for now, but it's just interface upgrade. OK, so now that we have a connection, what do we want to do with it? Let's do the simplest thing that will work. Let's take whatever gets sent on this connection, and let's copy it to our terminal, to standard error. There's a function to do that, and it's io.copy. Copy takes a destination writer and a source reader. And because interfaces are composable, indeed, the destination can be implemented, for example, by standard error, which is a file. A file has a write method, so it implements writer, so we can use it with copy. And then con, even if it's a net.Conn, it has a read method, so it implements the reader to be the source of our copy. And then we're just going to log, copied and bytes, and finish it with error equal %v. OK, this is ready to run. We can take this and go to a terminal and just go build and execute what we're building. We run it. Nothing happens because we're hitting the accept loop and we're waiting for a connection. So what do we use to test this? We can use an utility called net.Cat, which does nothing else than connect to something that is accepting connections, and just take what we type into the terminal, send it there. Nothing else. So we open it, and we say, hello, GopherCon. It does buffering by lines, so as soon as we send the line, there. We received it on the other side, and we copied it to the standard error. So this is already a network service. However, there is an issue with this. What happens if we make another connection while that one is running? So now we are here in the goroutine, right? We run accept, we got a connection coming in, and then we started blocking on copy. The problem is that now the accept loop is not running anymore. So if we take another net.Cat and try to do the same thing again, nothing's happening. Why is nothing happening? Because accept here is not running because we're blocked here. So indeed, if we close this connection with Control-D, we send the EOF, it will finish that connection, loop around, run accept our next connection, and copy what it had from there. Also notice how it ended with nil. That's because when a connection is over, it read returns EOF, which is a sentinel error, and copy knows that sooner or later it will hit a EOF. So if it hits a EOF, that's not an error, and it just returns nil. OK, so how do we fix this? Well, if you remember, we can just do it synchronously, but we have to tell the scheduler which are goroutines that need to run concurrently. So we're just going to take this code over here and move it into a function that takes a net.Conn. So we're going to call it copy to standard error. And it's going to be it's just going to do that. But what we're going to do instead now is that we're going to use the go keyword to start a new goroutine that runs with this function and pass it the connection. That's all it needs to serve this connection. So we save it, we recompile it and run it, and we try this again. First connection, and second connection. Now we have the scheduler doing all the work for us. So the code we wrote looks a lot like we would write with threading, because this is still blocking, and it's still linear. It does the copy, and then it prints a message. But it's the scheduler now taking care of scheduling that, such that in practice, it's the same kind of performance and the same model on the CPU as an event loop, where we don't have a single thread for each of these requests. These both run on the same thread, probably. OK, so this was this might have seemed trivial. You might say, yeah, I know about accept, so I know that I have not to read anything in the accept loop. But I'm telling you that this is a very common mistake to make, because usually you're tempted not to do all the work in the accept loop. You're tempted to do just a little bit. Like, you're tempted to say, I'm going to just read the first packet. I'm just going to read a header, so that then I can take the request and pass it to a goroutine ready to process. And it's going to work most of the times, because most of the times the client will have sent something immediately together with opening the connection. So you're not going to notice, and then in production, things will break when some weird client or some malicious user will just open a connection and do nothing. Your accept loop will break, will block, and no one will be able to connect again. Now, this is an example. We are inside the accept loop in this part of the code. And this is a patch for a security vulnerability in a popular DNS server, where it was accepting TCP connections and reading the request before dispatching it to the goroutines to be serviced. And this was assigned a CVE because it is indeed a security vulnerability when you let someone just connect to you, not do anything, and now your service is down and it can't accept connections anymore. So this is something to be extremely careful about. So to recap, we accept connections by opening a net.Listener and then calling the accept method on the listener. And we have to remember to never run anything else blocking on that loop. That goroutine will always be looping in accept, and it will always be accepting new connections to dispatch them and to create new goroutines. Now, before we move on, I want to show you something else. I want to show you how to implement timeouts. Why are timeouts important? The client might send a request, even send a couple lines, and then go away. Not send any reset, not send anything, just stop sending anything. They might do it because the network drops, or they might do it because they're malicious. But the problem is that while a goroutine is cheap, the resource that is now coupled with it, the file descriptor of the network connection, where a file descriptor is how you talk to the kernel and you both agree on which connection you're talking about, these are scarce. And if you've ever been woken up by a page with an error saying, no file descriptors available, sleeping 1 second, that timeouts is what you need. And if you haven't been woken up by that yet, it will happen. And when that happens, I want you to remember me. And you remember that I told you to use timeouts. Higher level libraries actually give you ways to do timeouts, but let's see how you do it with the primitives. So instead of using copy, we're going to write our own version of copy. We're going to write a loop that at every iteration calls setReadDeadline. The deadline is a hard stop by when everything has to happen in the connection or an error will be returned. So it's not a timeout that you can tell it 5 seconds. You have to tell it time.now, an absolute time, plus 5 seconds. And after that, we can just take a buffer. It doesn't matter what the size, because this is just the size of the chunks in which we're going to copy things. And we can just use our normal, our read interface. So we can do con.read onto the buffer. We're going to slice it because it's an array right now. It's an array so that I know how big it is, and it's allocated on the stack. It will probably do that anyway, but. And then we take the error and the n. This error is not a fatal error, because remember that EOF is an error returned from read. So here is where we put our concluding line. We're not keeping tally, so we're just going to put the error there. And if we did this correctly, we're just going to write it to a standard error ourselves. So we basically re-implemented copy, but with a deadline at the top, which is going to do an inactivity timeout. And important, we have to write only up to n, because read returns as soon as it can, because it's not obvious that the protocol can even proceed to read that many bytes. You might need it's in the first 100 bytes to then do something about it. So this can very much be less than 128. OK, so we're going to save this, and we're going to run it and test the timeout. And we're going to start sending for more than 5 seconds, and it works because we're not stopping. Then we're going to stop for 5 seconds, and it will hit a timeout error. However, the connection did not close. You know why? Because I did not return from the function. But it's important not just to return from the function, because that's not going to just close the connection as well. But you also have to defer a con.close so that the connection will be closed when we hit the timeout. This is because timeouts are recoverable errors at this level. There might be higher levels where after a timeout you can't reuse the connection, but at this level you could totally give it another chance and keep reading from the connection. That's actually what was happening. We could have kept typing. Actually, we still can. But if we now recompile the code as is, we can send stuff for more than 5 seconds, and then stop for 5 seconds. And this time it closed the connection, because it called connection closed, and it told netcat, yep, this is it, EOF, end of story, and the comment returned. OK, so now we know how to accept a connection, how to service it, and how we need to take care about timeouts. Let's build something a little more useful. Let's build something that we can actually use. We're going to build a simple proxy. A proxy is just a network service that takes data from a connection and sends it to some remote endpoint. For example, we're going to run a proxy that we're going to connect to with our browser, and it's going to take everything that's going over the wire without understanding it, and it's going to send it to GopherCon.com at the HTTPS port so that we can see TLS happen. How we do that is that we're just going to make a new function, which takes net.Conn as well. We're going to remember to defer connection close this time. And we're going to use the other main function of the net package to open a connection to a remote side. Net.Listen is to accept connections. Net.Dial is to open a new connection to somewhere else. It takes the same protocol identifier first, and then it takes an address. So for example, GopherCon.com port 443. If there's an error, we're going to log it and return. We don't want to fatal here because that would destroy also all the other requests that we're handling at the same time. And after checking the error, we're going to remember to name the connection something different, so remote, and we're going to remember to close it like that. So now we have two connections. We have one to the browser, and we have one to GopherCon.com. And we want to copy. So we can, again, use io.copy. But we need to do it in two directions. We need to copy both from the browser to the remote side. Remember that first goes to the destination. And we want to copy from the connection to the remote, from the remote side to the connection so that we copy the answers. Now, there's something here that should scare you a bit. The fact that I'm starting a goroutine and I'm not really keeping track of it. It's really important when you start a goroutine to know how it's going to end, with you paged or not. No, how it's going to end, how it's going to get closed. And you need to know what will happen. In this case, we're fine, because when any of the two connections closes, the copy will return, and the two con close will get deferred and run, and this will definitely return, and the goroutine will end. So here we're fine, but always keep in mind what happens when it's canceled, what happens when it's closed on only one side and not the other, because you really don't want to end up with a connection open to the remote and no one to service it for anymore, and you just leak that connection and you lose track of it. OK, so we are going to run this. And this time we're going to use a browser to connect to it. And nothing's happening because we haven't changed this to proxy. So we're still copying to standard error. But hold on, this is actually useful. What you're looking at here is TLS first packet. It's the opening salve of the TLS protocol. And notice how there's localhost there? That's because in the browser, we're connecting to localhost at the top. I don't know if you can see it, but that's the host we're connecting to. And remember this because this will come in handy later. But here, localhost in plain text right there in the middle of all the binary junk. Let's do it again. And this time, boom, we connected to something. Now, the server on the other side, when we asked it, hey, can I get localhost? Of course, went like, no, this is GopherCon.com. I have no idea what you're talking about. But it sent something back. So our connection is working. And not only that, but we also made a TLS handshake. It says not secure because they don't have a certificate for localhost, of course. But it does have a certificate for GopherCon.com. It's a bit small, but that's what's telling us that in our proxy, we are actually connecting to GopherCon.com on the other side. And the certificate is making its way through the proxy, from the proxy back to us. And the whole TLS connection is happening between us. OK? OK, so we built a small proxy, and that's it. And here's the beautiful thing. These, I don't know, 30 lines are an extremely fast TCP proxy that you can actually use. It doesn't have timeouts, so you probably have to decide what kind of timeouts you want on your proxy. But this is going to be as fast as Nginx, and not just because of the event loop. This, under the hood, is even using something called splice since Go 1.11. And what splice does is that you can tell the kernel to take stuff from one connection and copy it to the other TCP connection without touching it. It's not even copied into the proxy and out of the proxy. It doesn't touch user space. And this is happening all magically. We just wrote IO copy. But what's happening is that IO copy is, this is the IO copy function. We can go look at the source. Never use the network on a talk, folks. OK, we can go look at the source and see that it's upgrading the interface to writer to or reader from. And since TCP-Con implements reader from, it will get upgraded, and that will get called, and it will get past the other TCP-Con. They will recognize each other and say, oh, OK, you are also TCP-Con with a type assertion inside the net.Conn wrapper, and they will go, OK, we are on Linux, we are both TCP-Cons, we got asked to copy, splice. So those 50 lines over there are just as fast a TCP proxy as what the best thing Nginx can do, and we just wrote 50 lines of Go. And I'm not exaggerating. That's really all it can do, because it's not doing any work. The kernel is doing it all. I just love the interface upgrade in IO copy. Like, it's just beautiful. OK, so to recap, what I'm getting so excited about is that we just open a connection to the upstream with netdial, and then we use the IO copy in both directions to copy things back and forth. OK, so next, let's get our hands dirty. I wouldn't be giving a talk if I wasn't talking about TLS. And TLS is the S in HTTPS. It's what gives you the green lock in the browser. It's what takes care of encrypting any connections you do. And how it works is that every message you send is framed in a structure that starts with a couple obsolete things that we wish we could remove, but we can't. Then 2 bytes of length. And then a message of the length of those 2 bytes. So those 2 bytes tell us how long is the message. Because TCP is a stream, so we need some way to know how long the first message is before we start parsing it. And then inside there's a handshake message to open the connection. And the first handshake message is a client hello, which is the thing you saw on the screen all garbled. And one of the extensions of a client hello is the server name indication. That's what the localhost thing was. SNI is how the client tells the server which site it's trying to connect to so that it can load the right certificate. Imagine a server that serves 100 different websites on a single IP. It needs a way to know which certificate to load to present it. And that's SNI. So what I want to do now is write a parser. I'm not going to write a parser on stage for TLS. So I cheated and wrote one beforehand. But we're going to write a function that takes a connection and reads enough one TLS message so that we can extract that localhost thing in a way that we can parse. So again, first thing first, we defer closing the connection. And we put a deadline on how long we want to take to read the client hello. So for example, we set a read deadline of 30 seconds. OK, now that the connection is set up, we can start reading things. We're going to read them into a buffer, which is a bytes.buffer. And we're going to use, instead of copy, we're going to use copy n. It's the same thing, but we can tell it how many bytes to copy, and it will return an error if the connection closes sooner than that. Again, we can copy to the buffer as a destination and use the connection as a source. And we're going to copy 1 useless byte, 2 useless bytes, and then 2 bytes of length, because that's the very first part of a TLS message. I'm going to check the error. And then we're going to parse those 2 bytes into a number of bytes that we need to read next. And for that, we're going to use the encoding binary package with the big endian order, because that's the order in which the 2 bytes are. And we're going to, make it a uint16, and we're going to tell it that it's from the buffer bytes, and it's from the 3rd byte, because the first 3 are completely useless, to the 5th byte. And then we're going to do the exact same thing to copy to the buffer the actual message. Ooh, this was going to be bad. OK. And then now we're copying the whole message. So now we copied the entire client hello, that first structure, which has the SNI in it, into a buffer. And it's complaining because it wants an int64 here. OK. So now that we have that, we cheat and use our pre-written parser, which I wrote with CryptoByte, which is this wonderful parsing library. And folks, wonderful and ASN1 parsing don't usually go together. But it's a wonderful parsing library that allowed me to write in 30 minutes a client hello parser that does 0 allocations. It's beautiful. And it will catch any malformed client hello, even if I'm not actually parsing most of the stuff. So parse client hello, and we're going to pass it the bytes of the buffer. And if it parses OK, then we're going to print got a connection with SNI %q. %q is great. It prints something quoted, so that if there's binary stuff in there, it's going to get escaped. Beautiful. And at the end, we're just going to return, which is going to close the connection, because we don't care about doing anything else with the connection for now. Let's start it. Let's reload over here, which is going to break. And it's going to say that it's a connection closed, which is what we wanted. But over here, boom, we received a TLS message, we parsed it, and we wrote that, we extracted the SNI from it. So again, we set a timeout, read the header, read the message from it, and then parse the packet. This is really how you start most complex protocols. Now, let's make our life a little harder. What if we want to both parse SNI, and after we parse the SNI, proxy the connection? Now, we could just use proxy over here, just call it immediately after. But that's not going to work, because we already read stuff off the wire. The connection will not replay the client hello for the proxy side. So the other side will just receive something without the beginning, and it will not know how to open a TLS connection, and it will break. So the first part is in bytes.buffer. And that's why I use the bytes.buffer, because a bytes.buffer is both a writer, so that we can add to it, and a reader, so that we can read from it. And there is a beautiful function in the standard library called multi-reader. What multi-reader does is that it takes multiple readers and returns one wrapper reader that when you read from it, it reads first from the first reader, then from the next, and the next, and the next. We only have 2. But this way, we can put first the buffer as a reader, and then the connection, so that when the proxy starts reading from it, it will read first the client hello we have in the buffer, and then it will carry on reading the rest. Now, but we still have a problem. We don't want a reader, we want a net.Conn, because that's what proxy takes, right? So what we're going to do is a very common pattern. It's called net.Conn wrapper. We're just going to make our own type, a prefix con, which is a structure with a net.Conn embedded in it. When you embed things like that, all the methods get promoted, so that when you call a method on prefix con, it gets dispatched to the net.Conn you put inside it. But we're also going to put inside a reader. And then we're going to instantiate it with a connection that has as con our connection, and as reader our io.multi-reader, which first reads from the buffer and then reads from the connection. And then we're going to reset the deadline. This is important, because we had set a deadline above here, and now the proxy will run for longer than that, so we want to reset it and let the proxy deal with it. And we do that by passing an empty time to set read deadline. And then we're just going to call proxy on C. Now, this is going to break. It breaks because prefix.con.read is ambiguous. When it tries to read from it, it doesn't know whether it's reading from net.Conn or whether it's reading from the IO reader we just instantiated. So we're just going to make it explicit. We're going to put a method here, which takes precedence, and it's going to be read. And it's going to return int and error, just like the reader interface does. And it's going to return specifically from the reader read. So now we're intercepting the call to read before it reaches the connection, and we're sending it instead to the multi-reader, which is going to first read from our buffer that we filled with the client hello, so that the connection gets put back together into a whole before being sent to the remote. So let's try this out. It worked. The proxy worked, and at the same time, though, we are still parsing SNI. Now, this already would be an extremely useful service, because you could decide where to send that connection based on the SNI. So we wrote in 100 lines, less, we wrote a TCP proxy that can understand TLS, parse it, take the SNI, make a decision based on that, and send the connection to a backend for processing. And to recap, we did that by making a net.Conn wrapper, which is our own structure that intercepts some of the calls to net.Conn. Now, let's step it up a notch. Let's try to serve TLS ourselves. Now, I didn't show you net.Conn wrappers just because they're useful when you're building your own, but also because they're a common pattern to understand what many libraries, higher level libraries that you're using do. And TLS Con, the TLS implementation in CryptoTLS, the standard library, is a net.Conn wrapper. It does the same thing where it intercepts read and write, and on your first read, it's going to do all the handshake, all the key establishment. And then on every other read, it's going to decrypt things. And on every other write, it's going to encrypt things. And notice that there's no extra goroutine involved here, and there's no channel involved here. Because you want these wrappers to be as sealed around it as possible, so that close and all cancellation, you don't have to worry about canceling all of this. When your client is going to read from a TLS Con, it's going to block, while the TLS Con does all the processing of the handshake. So let's see how to use it. We're going to just make a TLS Con, just like we made our prefix con, by saying that we want to make a TLS server, because we are on the receiving side of the TLS connection, and by wrapping our C connection and passing it a TLS config. The config is there to have a certificate, and the certificate we're going to parse with load external keeper from just a file. In production, you would probably use something like autocert to get one from Let's Encrypt. One file for the certificate and one file for the key. Normally, you would not do this on every connection. You would do this in the main before you start your service, and then you would pass it into the function. But we're just writing an example here. And finally, we're going to make a config, which is a tls.config structure. It takes many, but in our case, we are just going to give them the one. And then we can do whatever we want with this TLS Con. We could copy it to standard error, and then we would see the contents decrypted from the connection. we could proxy it. So let's start by using copy to. This is the beauty of having a net.Conn interface. We can compose all of these things, and now we're using first the multi-reader wrapper to make it put it back together, and then the TLS server wrapper to make it decrypt, and then we're copying to standard error. We're going to try running this. We're going to try loading the page, and it's going to break because it doesn't have a certificate. Making certificates for local development is a pain. And I'm not promoting my own tool, but here it is. It's called MakeCert, and I have stickers. But what MakeCert does is that it just makes a CA, installs it as trusted only on your machine, and then it lets you create certificates that are trusted only by your machine with a simple command. So you can just say, I want a certificate for localhost. And it's going to make the 2 PEM files. And then we're going to run our program again, reload, and boom. We had our TLS server decrypting the connection and taking the HTTP out of it and displaying it to standard error. But just like we can copy it, we can proxy it. But now we don't proxy it to 443 because we're doing TLS ourselves. We proxy it to 80. And when we reload this, we get the same error, but look in the corner. There's a green lock, because now the whole certificate processing and all the TLS processing is being done by the proxy, which is decrypting it and then sending it over to the backend for processing. So to recap, we started by accepting connections with a net.Listener and calling accept on it. We looked at how to set timeouts on it. We looked at how to copy things in and out of it. And then we looked at how to proxy things by coupling copy. We then looked at how we can use net.Conn wrappers to intercept some calls and make the behavior of the net.Conn different. And we looked at how TLS Con is a net.Conn wrapper. And we used it to build what is effectively now a TLS decrypting reverse proxy, the kind that you find in some infrastructures where you have the load balancers on the front that accept a connection, decrypt TLS, and then send the HTTP request to one of the backends for processing. And we wrote that in 100 lines of code. And this is going to be just as fast as Nginx could go, because it's going to serialize our connection, our work, schedule our work as if we had an event loop. And it's even going to use kernel features to make the proxying faster. Not with TLS, but I promise you the TLS package is pretty fast, if I say that myself. OK, so thank you very much. And if you take anything away from this talk, it's that when you're going to get that page, and it's going to say out-of-file descriptors, you will remember me, and you're going to Google Timeouts. Thank you very much.